Right, folks. I'll begin with a short story. I was actually hoping to finally record the talks this time because we get asked a lot about the recordings, and I actually brought a tripod, iPhone, a bunch of stuff, or a wearable mic. But I then realized that we are at Cisco Meraki. This room has more equipment for recording than any other place in the world. So it has a bunch of cameras here and over there, and it's doing something where it's kind of capturing the speaker as you move. So all of our speakers, you should be comfortable moving right here. So that being said, we're going to have a recording of this. So this is cool. Yeah, all right. Now that we are here, thank you so much for coming. Welcome, welcome, welcome. So my name is Irina. I'm super excited for each of you coming here today and reconnecting with old friends, making new friends. This is the main goal. But we also have a huge agenda today. We're going to be learning a lot. And I'm going to say we're going to be learning about all the different aspects of Ruby and Rails. And we are here, first of all, thanks to Cisco Meraki. Thanks for hosting us today. We're going to hear more about that in a second. And we'll learn about time series data from Liz. Then we'll learn about Postgres optimization, which is the number one thing you need to learn about performance optimization in Rails from Lukas. And then we're gonna talk about infrastructure, about Dokku, and something super exciting about writing a C extension from Cameron. And finally, James is going to tell us about, we're going to talk about front end and some inspiration from React. But that's a few words about myself. I'm only going to be referencing to the screenshot from now on. My keynote at RailsConf was just uploaded a few days ago. You can actually watch it. Thank you. So I'm the CEO of Evil Martians. We work with startups. We help them build and scale their products. We mostly work with developer-first products, and this is just a few examples. And we also build a lot of open source. So you might know us from AnyCable, TestProf, LeftHook, Image Proxy, PostCSS, and a bunch of other stuff. Ruby Next. Anybody? Any Ruby Next fans? Now, there's something special. There are two special things today. One is Andrew Atkinson reached out proposing to give away a couple of his books. And this is what we're going to do. So you guys probably know about his books, about performance, high-performance Postgres for Rails. We have a couple of them, and we also have another great book from my colleague, Vladimir Dmitriev, Layered Design for Rails applications. So this is what we're going to do. There is a survey. What I'm thinking is, yeah, please maybe I will upload the slides later to Luma, but yeah, you can check the URL. So what's happening is that we have a pretty cool community here already. So this is meetup number, I don't know, 4 or 5, difficult to remember. But the survey is to collect new ideas and collect feedback and figure out how we can interact and help each other more. So please propose ideas, and you can check if you want to take part in the giveaway, and then we'll randomly select people who will get the books. So please do this. And finally, if you've been with us last time, if you remember, I shared an idea, and it was this idea. A special event. I wanted to do a special event about Ruby at Y Combinator startups because, well, we know Ruby's not that popular these days in San Francisco. So we want to remind people about successful startups building with Ruby, which was the title, the topic of my talk at RailsConf also. And I said something like this. And you know what's happening?
Wow.
So basically, the next meetup is going to be at Y Combinator itself. So this is a fresh registration link, and go check it out. I will say, because this is Y Combinator, they're asking more questions. They will be asking you of like years of experience with Rails and stuff. But I'm gonna say they are doing this because they are really looking for Ruby engineers. And a bunch of YC startups that are gonna be speaking are also looking for Ruby and Rails engineers. So it's gonna be a cool event. And with that, I'm happy to give it away to Ronan, who is gonna tell us a bit more about Cisco.
Thank you, Irina. Right, yeah. Welcome to Cisco Meraki. Thank you, Irina. This is super inspirational. Yes, like a couple of like Ruby meetup. We are like just like you are restarting that. I'm like super happy to participate in like 3 or 4 last ones, and super happy to be able, on behalf of Meraki engineering team, to welcome you here and like making like Cisco Meraki a sponsor of this meetup. Yeah, so just wanted to talk about a little bit about Meraki for whoever is not familiar with Meraki. That's why we ask you like a couple of questions first. We gathered a little bit of data, and thank you so much for like answering the questions. Did you know that Meraki uses Ruby on Rails? Like personally speaking, when I got hired, I got recruited by a recruiter, and he told me like, oh yeah, like, are you interested to work for Cisco? And I was like, Cisco, like Ruby, Rails? Are you sure you have the right profile? I was like, yeah, let's jump in the call. And then like he told me like, oh yeah, do you know Meraki? And I was like, ah, Meraki rings a bell. That was my Wi-Fi when I was at the startup that I was working on. So I was like, okay, cool. And then like he says like, yeah, the whole dashboard is in Ruby and Rails. I was like, whoa, Ruby and Rails at Cisco. That's awesome. So yeah, turns out that 59% of people knew that. The rest know it now. Yeah, we are a big shop. We have a really big dashboard and Rails application. And we have like a lot of engineering. They don't all work directly on Rails. But out of these 2,000 engineers, half of them probably work on the application. So talk about the monolith going really a long way, right? The dashboard is pretty nice. We are making billions of dollars out of it. So and we are like a great asset. Cisco can't like have enough of us. So like they are really happy with their acquisition and what results we bring to Cisco. And today, like the Cisco Cloud is Meraki, right? So like we like made the dashboard built on Rails, the Cisco Cloud. Like just imagine a little bit of that. Like this is pretty crazy. So we're bringing like so I'm gonna go on like what's the stack and everything, but we're bringing like historic Cisco switches and firewall and everything. Like historically, these devices are like on premises. We are bringing that to Meraki into the dashboard. So like for Rails engineering and like for like people that are passionate about like system of information like myself and you all, I imagine, like this is very exciting. So yeah, I'm really happy that now you all know about like the engineering at Cisco. So yeah, what is Meraki? I just touched on it, but like just to go back to the roots, like this is, the word means like something done with soul, creativity, or love. And this is really our mantra. Resume really quick, I'm not going to bore you with that, but like we're born out of like a project at MIT, founded in 2006, and 6 years later, acquired by Cisco Systems. And what we're offering is like a full cloud solution of a network for enterprises. It goes from like registering your devices to having switches to having Wi-Fi, all the suite, and you are like, you can be ready really easily with Meraki. It reaches out like 2 million of active networks today, probably more, like this is
5 billion.
Yeah, way more. And 7 million devices online, and yeah, that many employees. We have a new location in Bangalore as well, but this is where we are in the world. Of course, like this is only Meraki. We are Cisco, so like this is even bigger. What is the Meraki magic? Usually what customers like is that this is magic. So of course, we are engineers. We know it's not magic. We work really hard to make it magic to the customer. But that's what we like about information system, right? When it works, right? When you can like order your train ticket like without like even thinking that it's a system of information. It just works, right? So that's what we really want at Meraki, making it work. You can order Meraki, configure it in the cloud, configure like the network, everything. You don't even have the switches in your backyard or in your like in front of your door. You don't have anything. You can configure all your network. Then you receive the thing, you plug it in your facility, and then boom, you have the network ready. This is really cool. That's what we call Meraki magic. And it's really true like inside Meraki as well. Like Meraki is really cool to work at. People really believe in what we are doing, and this is like cool in day to day, like to like work for this company. So really happy to be here and presenting that to you. What's the full stack? Well, we have everything. We have like MS and MR, like which is switching. We have MX, which is firewalls, and like protect you from like the internet inside. And then we have also MV, all the camera suites, and MT, which are like all like sensors, like temperature sensors and like door opening sensors and buttons and everything. Very like a full solution for your company. Yeah, our customers are like goes from government to like global enterprises, non-profits. It's right now the Olympic Games, so like Cisco is right there. Meraki has a role there, and yeah, we run main streets, small businesses as well. I don't know if you so sometimes like you go to a coffee and it's written at the bottom like like connect, and then it's written like powered by Cisco Meraki, which is really fun to spot on the day-to-day. Yeah, our values: simplify everything, care deeply, everybody in, and be brave. I'm not gonna go into details, but like if you resonate with that, like we are recruiting, so don't hesitate to like talk to me, or like, there are a lot of Meraki around here, so don't hesitate to talk to us. Yeah. Is there anybody having any question or want me to?
Which Rails version are you using?
It depends of like which application do you want to talk about. Last application is Ray 7. Yeah, the monolith though, not there yet. We are still at Rails 4. Turns out that like when you build like we started at Rails before Rails 1, right? Like this monolith has like a long life, and priority of like upgrading was not always there. It is now, but we have like to catch up a lot. So yeah, we are actively working on it. And you know, like as a business, like when you go to Chuck and say like, hey, you know, Meraki, it's really cool, but we need to upgrade Rails. And he's like, I don't care, just deliver this feature instead. So, you know, it's always like a thing that you need to like make a priority and make it like super interesting and valuable for the business. And yeah, that's about it. But yeah, we're working actively. I think after Rails 5, it's going to be an easier way. But 4 to 5 is like, yeah, a big gap. Yeah.
We have it working on Ruby 3.3 at least, so that's the good news.
Oh yeah, that's true. We're on Ruby 3.3. And when I joined, it was Ruby 2.3. So yeah, huge effort there. And yeah, it paid off. So yeah, I think this time for Liz. Thank you very much. I've been Ronan. I'm a Meraki software engineer for 3 years here. And yeah, talk to me if you want to know anything. Thank you.
Hello, my name is Liz. I'm a software engineer on the switching team at Cisco Meraki. Prior to Meraki, I worked in startups ranging from Series A to IPO. I live about 5 hours north of San Francisco in a funky little town called Eureka. Honestly, it's quite possible that I'm just using this presentation as an excuse to post all the cool photos I don't know what to do with, like this near miss with a pelican in Mexico. But obviously, I also want to talk your ears off about time series data. It's a topic that Cisco Meraki deals with quite often, and I found that the gotchas and intricacies can be difficult to uncover at first. By the end of this talk, you'll hopefully have an understanding of how time series data might differ from the typical sort of relational data you might be used to dealing with. I'll walk through how to select a tool for managing time series data, how to organize, query, and aggregate time series data, and how to translate your design to API constraints. Before jumping in, you might be asking yourself, what even is time series data? Time series data is essentially just a collection of observations recorded over consistent intervals of time. This graph, lifted from our dashboard at Cisco Meraki, shows a usage rate in bits per second for a device over time. We record this data every 5 minutes by polling the device, store it in a time series database, and display it in a convenient graph over time. Time series data has become pretty ubiquitous as we collect more and more data to model our surroundings and predict trends. Devices like smartwatches have introduced amateur athletes to way more data than they've ever had access to. Our friend Liz, inspired by apps like Strava, wants to track her surfing as well. Liz has just taken her first surf lesson, and she's keen on learning how her surfing will improve over time. She's decided to record this data in a time series database and to access it via an API endpoint. But where does she start? In surfing, it's important to select a surfboard that's suited for a particular swell. If the waves are steep and powerful, it might be worth breaking out the shortboard for better maneuverability. The same is true of databases. It's important to select a tool that's appropriate for the type of data you plan to deal with. Time series data often comes in large quantities, and efficient access is highly important. So a database that can accommodate these concerns is crucial. When selecting a tool for managing time series data, you have 4 options that nicely mirror the options a surfer faces when deciding what board to surf. As a surfer, you can surf a board you already have. This is applicable for folks who already have a dedicated time series database in their tech stack. As a surfer, you can use an old board, but add a new set of fins. This is analogous to using a database extension for, say, Postgres, adding on to a tool you already have. As a surfer, you can buy a new board. This is similar to adopting a new database technology dedicated to time series data. Or you can break out the foam and fiberglass and shape your own board. This is just like designing and implementing your own time series database. It's quite possible that you already have, as part of your tech stack, a database that works well for your time series data use case. In that case, you just have to ensure that you're using your database tool correctly with the proper techniques. Later in the talk, I'll cover techniques for the proper storage and querying of time series data. Or maybe your team already uses a more generalized database like Postgres, and the best solution in this case would be to add a Postgres extension. This is similar to buying a new set of fins for the surfboard you already own. Fins are easily swapped out without changing the surfing experience too much. In this case, the old board is Postgres, and the new set of fins is an extension you can use with Postgres. There are several options for time series extensions you can use with Postgres. 2 of the most notable options are PG Time Series and Timescale DB. These extensions provide a user experience around creating, managing, and querying time series data, which doesn't come out of the box with vanilla Postgres. There are many benefits to using extensions. Using an extension is lower lift and cheaper, Plus, you're already used to surfing the board. Using a Postgres extension will reduce the learning curve and augment the speed of development while avoiding the performance hit you'd otherwise take with vanilla Postgres. A further benefit to using a Postgres extension is it will be far easier to join relational data with time series data as needed. Sometimes your existing tools don't cut it and you need to invest in something entirely new. This is analogous to buying a new surfboard. If you're looking for a dedicated time series database, it might be worth looking into solutions such as ClickHouse. ClickHouse pitches itself as a fast, open source analytical database designed around time series data. Managing time series data is all about optimization, and each tool is optimized for a different ideal use case. It's essential to evaluate your conditions before selecting a surfboard. In the same way, it's important to consider what type of data you'll be working with and what you'll be doing with it. According to users, the Timescale DB Postgres extension is faster with smaller batch sizes, whereas ClickHouse is more performant with larger data sets. Read up on the documentation for the tool you're considering, but also take a look at user feedback and maybe conduct some performance tests of your own. Sometimes, no available database seems suited to your highly specific needs. If your use case is really particular and you're feeling especially industrious, you might want to just break out the foam and fiberglass and shape your own board. Meraki found itself in this situation in 2008. Our core product is a cloud-managed platform that allows users to configure and monitor their networking devices. The monitoring data is, more often than not, time series data. We track metrics such as packet count received by a switch, the temperature of a device, or the device's memory usage. Trends over time can give insight into the health of a system. In 2008, there were far fewer time series solutions available, so a team at Meraki developed their own, and we call it Little Table. Little Table is a relational database optimized for time series data with data clustered for continuous disk access. For ease of use, Little Table includes a SQL interface for querying. The team wrote an excellent white paper on Little Table, and I've linked it in this slide. I can't recommend it enough for anyone who wants to really understand the intricacies of time series data. If you Google Meraki Little Table white paper, it'll come up. All right. Now we have our board picked out, we understand the conditions we're surfing in, and we've landed on a board that works best in those conditions. However, the work is far from over. You can have the perfect board and still struggle to actually surf if you don't have the proper technique. Technique is also incredibly important when dealing with time series data, regardless of which database tool you choose to use. In order to optimize performance, it's crucial that we follow some tried and true patterns for organizing and querying data. The time series techniques I'll cover in this talk are data arranged by time, hierarchically delineated key, querying by index, and aggregation and compression. The identifying characteristic for a time series database is that it organizes data by time for efficient access. Most databases like ClickHouse will automatically generate an index on the timestamp column. This allows for the most performant access when retrieving data for a range of time. Because of this unique structure, some databases enforce restrictions. Arranging data by time allows for highly efficient reads, but writing can be quite inefficient. The designers of Little Table decided to constrain writes to be append only. Since we're collecting data over time, it doesn't make much sense to spot fill historic data anyway. The second important concept of time series database design is something Little Table calls a hierarchically delineated key. This is basically just a fancy term for a composite key whose components are organized at increasing levels of specificity. A very similar pattern is used in ClickHouse. The composite key determines how the data is arranged in the table, in addition to being grouped by time. This hierarchical organization enables efficient queries as long as you're querying based on ordered components of this key. In order to determine the components of this key and how they're ordered, it's super important to understand how this data is going to be accessed. Your queries will only be performant if you're accessing a continuous block of data. It's probably best to visualize a real-world example in order to understand what a hierarchically delineated key is. Here's an example lifted directly from the Little Table white paper. As you can see, the data is organized along two axes. On the x-axis, we have timestamps, and on the y-axis, we have the elements of the composite key. You'll see that along the y-axis, all the records for a single network are grouped together, and within that network, all the records for a single device are grouped together. This organization could be as many layers deep as you want, but in this example, we just have 2 layers. As we saw in the previous example, the most important takeaway for a hierarchically delineated key is that its components are organized with an increasing degree of specificity. The example from Cisco Meraki included 2 components, network and device. Since a network has many devices, the example is purely hierarchical. However, just because the ordering in this key is typically hierarchical, that doesn't mean it has to be. The organization of this primary key depends only on how the data is accessed. Liz's surfing application is designed to be surfer-specific. While we want to store data from multiple surfers, it doesn't make much sense to query the data across many surfers, since each surfer is interested in their individual progress. In this case, we can prefix our primary key with the surfer so that all the data for a single surfer is co-located in the table. Then we can follow the hierarchical pattern with a region and a break. The region might be, say, Los Angeles, and the break might be Malibu First Point. The region and break are very similar in concept to the example from Cisco Meraki, since a region contains many breaks. Now that we have a key that's optimized for querying, we need to actually write our queries in the most optimal way. This data is highly structured, and the way it's structured depends entirely on how we plan to query it. Hopefully you remember this graphic from a couple slides ago. Once again, I think it's easiest to understand this query by visualizing it. As a refresher, data is arranged by time across the x-axis and composite key across the y-axis. When querying time series data, it's essential to include the timestamp in your where clause. It really doesn't make any sense to query this data without a timestamp or a range of timestamps. Additionally, you'll want to include part or all of the elements of the composite key. Because of the way the data is arranged in little table, you only ever need to include a prefix of the composite key when querying. This means that you could query all the data for a single surfer over a range of time, or you can query all the data for a surfer in a specific region over a range of time, or you can drill down with the entire composite key and request data for a surfer, region, and break. ClickHouse is a bit different. The data in ClickHouse is not arranged across 2 dimensions. Instead, the timestamp is basically the final component of the composite key. Because of this, it doesn't make much sense to include just the surfer and timestamp in the query because you're skipping the middle section of the primary key. Consider the example I've shown. We have a contiguous stretch of data for Liz, which is broken into region, which is then broken into break, which contains all of the timestamped records for, say, the last month. It doesn't make much sense to query the data for Liz over the past 2 weeks because the data here is not contiguous. For each location, you'll have to grab just a section, skipping over the data points that don't fall within the requested time span. The only performant query for ClickHouse would include all components of the composite key. You must specify the surfer, region, break, and a range of time. So it would be performant to query Liz's data for Malibu in LA over the past 2 weeks. It's important to drill down and understand how the data is arranged in your time series database of choice. By understanding the structure, you can visualize what a contiguous chunk of data looks like, and you can ensure that your query is making use of the way the data is structured. It's worth noting that once you execute that performant query, as long as that quantity of data is reasonable and can be loaded into memory, you can always write a subsequent query that gets the data you want. It's important, though, to make sure that that first query is performant, or else we're losing the benefit we get from a dedicated time series database. Cool. At this point, we know how to store our data and how to query it. We can now start to look at the maintenance side of things. Here's the thing. Liz surfs a lot. She plans to surf for years to come, and though we'd love to keep all of Liz's surfing data in perpetuity, we simply don't have unlimited storage. When dealing with time series data, you have to balance 2 major concerns. You don't have unlimited storage space to keep raw data forever, but you also want to provide the user with as much data as possible. In order to solve for the first concern, the fact that we don't have unlimited storage, we need to take a look at data retention. Every time series database that I've seen includes some sort of policy for data retention. Often this comes in the form of a TTL, otherwise known as a time to live. The time to live dictates how old the data in the table is allowed to be. After a certain point, data of a certain age is simply dropped from the table. Now we also need to address the desire to show as much data as possible, and in order to do so, we need to extend the TTL as much as possible without sacrificing storage. There are a few ways of going about this, notably compression and aggregation. Compression is the method of choice for the Postgres extension timescaledb. When you add data to your database, it is in the form of uncompressed rows. Timescale uses a built-in job scheduler to convert this data to the form of compressed columns. You can see in the first example on the slide what 6 data points might look like compressed into a single data point. This preserves all the original data while restructuring it into a format that requires less memory to store. I noted early in the presentation that the makeup of the composite key should be determined entirely by how the data is going to be queried. The same is true of compression. The way the data is segmented depends entirely on how it's going to be queried. If you're most often accessing data by, say, device ID, you can configure the scheduler to compress data by device ID. The second example in this slide shows an example segmented by device ID. There's a second approach to ensuring that we can preserve data for an extended period of time without increasing our storage costs. This approach is called aggregation, and this is the methodology of choice for Little Table. When we're speaking about aggregation, there are two concepts, the base table and the aggregate table. The base table is where we insert the raw metrics we're recording, and the aggregate tables store a summary or average of that raw data. So first, we need to decide what raw metrics we want to store in our base table. If you recall, we already decided on a primary key that contains a surfer, region, and break. Each record will represent a single wave the surfer caught at that break at that specific time. At the most basic level, what Liz might want to know is how good was that wave? How long was she on it, and how far did she ride? And now, the aggregate table will have to contain a summary of the data in the base table. It might be helpful to know the total distance summed across all waves, the total duration summed across all waves, the maximum total speed for a single wave, and the number of waves caught over that time period. Now that we've decided what data to store in these aggregate tables, we have to decide what intervals of data make sense. These will determine which aggregate tables we want to create. This will also help us decide on our TTLs, constraining how much data we're actually storing. Since Liz tends to surf at most once a day, it makes sense to aggregate data up to the day. That way we can preserve data for each surfing session up to a TTL of 6 months. From there, we can aggregate up to the week and the month so that it's easier for Liz to track seasonal and annual trends. This leaves us with a base table with a TTL of 1 month, a one-day aggregate table with a TTL of 6 months, a one-week aggregate table with a TTL of 1 year, and a 1-month aggregate table with a TTL of 5 years. Woo, the hardest part is over. Now that we have our data stored, aggregated, and easily accessible, we want to design an API endpoint that Liz can use to easily query her surf data. The decisions we've made when it comes to querying and aggregation will determine exactly how the API endpoint will be used. The next step is defining an API contract which can be clearly documented for the end user, validated, and enforced. A crucial element to document for the end user is a set of allowable query params. The components and ordering of the composite key determine which query params are required and which are optional. As always, a time span is necessary for a user querying a time series database. Assuming we're using Little Table as our underlying storage option, we only need a prefix of the primary key, so the surfer is the only required component of the key. Beyond that, you can optionally specify a region and a break. It's important, though, to document and enforce that a user must also provide a region if they want to provide a break. Recall earlier that we noted you can't skip fields in the middle of the primary key. You must provide a full prefix of the primary key, which in this case is surfer, region, and break in that order. Now that we have the user's request, we need to determine which aggregate table you will be querying from. This requires an understanding of some terminology. At Meraki, we discuss time series data in terms of a time span and an interval. So I'll quickly explain what we mean by each of those terms in this context. The time span describes the full period of time over which we want data. Since our longest TTL in the database is 5 years, we can't query data for a time span that extends further than 5 years in the past. The interval corresponds to the grain at which the data is aggregated. The only options here are 1 day, 1 week, and 1 month. As noted before, each aggregation interval will be stored in its own aggregate table. We'll have a 1-day table, 1-week table, and 1-month table. In designing this API endpoint, we'll assume that the user wants the most data possible for the time span requested. This means that the TTL will determine which aggregate table we'll query from. We'll want to query from the aggregate table with the smallest interval whose TTL is still greater than the time span requested. So if the user requests a time span less than or equal to 6 months, we can return daily surf data. For a time span between 6 months and a year, we'll return weekly data. And for any time span between 1 year and 5 years, we'll return monthly surf data. And we'll validate that the user is not allowed to query the API endpoint with a time span greater than 5 years, since all data is dropped after that point. Now, I'd like to quickly show what a visualization might look like for time series data now that we have in mind the concepts of a time span and an interval. On this slide is another screen grab from Cisco Meraki's dashboard application. Here you can see that at the top of the page, there's a drop-down option for selecting data over the past 2 hours, day, week, or month. Those are the selectable time spans. We currently have the 1-month time span selected, and in the usage graph below that, you can see that the data is broken out day by day. In this case, for a 1-month time span, we're showing data over a 1-day interval. This pattern is especially helpful when you want to detect trends, since trends can be found when looking at data down to the hour or over the span of an entire month. Sweet. Liz now has easily accessible data on her surfing performance, broken out by break over time. Fast forward several years from now, Liz has been surfing for quite some time, and she's learned some important lessons. For example, she took a look at the monthly data for her favorite break, and she realized that she catches far fewer waves there in the winter than she does in the summer. And the waves she does catch are way smaller and peter out quickly. It turns out that this surf spot only catches south swells, and south swells are way more common in the summertime. Liz had no idea that swell direction was seasonal. It had never occurred to her to check. Now she knows where to surf in each season, and she's been able to update her surf routine accordingly. She's been catching way more waves, and she's been having a lot more fun. Looks like Liz is on her way to getting pitted. And that's all I have. Thanks so much for coming. If you have any questions, feel free to chat with me afterwards. Enjoy the rest of your evening.
Okay. You know how people say that Ruby is slow? Have you heard that? Ruby is slow. Ruby is slow, right? No, never heard about it.
It won't scale.
It won't scale. Yeah. But truth is, it's not Ruby that is slow. It's your database. And it's not database that is slow. It's your database requests that are slow. Let's talk about this now. Okay, folks. Okay, thank you. Yeah, let's begin. And I'm incredibly excited to listen to this talk right now. And Lukas, tell us more and make us a little bit better engineers, if you can.
I'll try. No promises, though. All right, so timing, 6:17, maybe 6:40. Are you okay with that? Okay, cool. I'll make sure to get you to a break and to drink some more chatting about Postgres or other databases, time series data, all the good stuff. All right, so I want to talk about how to optimize Postgres queries. Why am I talking about that at a Ruby meetup? Because I am a Rails Ruby developer myself since 2007, so I've worked with both Rails and Postgres for a long time. Many years ago, I used to be the engineer who had no idea what Postgres. I'm no longer in that state, but certainly I do learn things every day. And so I want to essentially share some of my mental model that I've built over the years on how to optimize Postgres queries. This is really about debugging, right? So I want you to essentially take away some ideas on how you can debug a slow query. And when it's Postgres, or maybe it is Rails after all, or other Ruby frameworks. All right, so we're going to talk about 5 things. The iterative process of optimizing a query, how to interpret explain, and specifically explain analyze buffers, which is your main debugging command in Postgres. How Postgres does cost estimation and selectivity. We'll look at a little bit of Ruby code in the beginning, and then we'll show some C code. Don't be scared. Postgres C code is actually very readable. Fourth, we'll talk about join order and parameterized index scans, and then I'll leave you 5 actionable tips as the 5th item. What's my process on iterating? What's my process on how I optimize a query? So as a background, right, like usually we start with something closer to this, if I'm a Ruby engineer or Rails engineer, which is a bunch of code. And you can see here, for example, I have a nice .each, and then I'm doing a .find, which is essentially a very simple select query, and I'm doing a bunch of other stuff here. So the reason I want to mention this, right, is because this, for record, is a screenshot of the source code of pganalyze, which is a tool to optimize Postgres. But I'm not here to pitch you on pganalyze. There's no slide that does that in the slide deck, but feel free to ask me about that afterwards, what pganalyze does. However, we use Rails, and we have code like this. And one thing you will notice here, if you looked at this in a tracing system, is that this kind of performs like this, which is a lot of really fast queries, but there's a lot of them, which is the n+1 problem. Right? Which here essentially is you have the .each and you have the .find, and you're not doing that essentially altogether. We're not going to talk about that problem today, but I want to call out that many of the problems I see with Rails are oftentimes n+1 problems, and so you should be aware of the difference between that and a bit hard to read probably. And if different tracing system, this is actually from our own tracing system, Honeycomb, which shows a slow query. The difference there is that you essentially have a very long span, which shows, this SQL statement has run for 20 seconds, and you essentially have this magic box called the database that, just does something in those 20 seconds. And so really, this is my goal, to essentially help you understand better how you can, find the root cause of slowness that looks like this in a trace. All right, when I optimize a Postgres query, it looks a little bit like this. Again, hard to read from a distance, but essentially it's a big SQL statement, and in the beginning I put explain, analyze, buffers, which is essentially that's the most common way you would actually understand what Postgres is doing. Explain is the main command here. Analyze buffers are the two options you're essentially passing along there. What this gives us, and you've probably seen this before if you've tried to understand Postgres performance, is you get a text output like this. There's also a JSON version for machine-readable format, which tells, in this case, nested loop, CTE scan, index-only scan, all the good stuff. This tells you what the database is thinking of doing, and then if you add the analyze option, what the database has actually done in terms of how it gets the data, how it joins the data together. This is really the core thing you want to have. Now, I'd like to quote Tom Lane, who's one of the principal authors of the Postgres Planner. And the nice thing is Tom actually, there's lots of mailing list discussions. Tom has lots of good input on, how to optimize queries. And one thing I find, interesting about what he's, said in a talk, I think many years ago, PGCon 2011, is that he essentially says the planner, like the Postgres planner task is fuzzy, right? So it's not like there is a perfect plan. There are trade-offs to consider. And so we'll oftentimes find the suboptimal plan because the planner couldn't, spend a lot of time on it, right? Because it's like trying to do this quickly before it executes the query. And so the Postgres planner, important to understand, it tries to find a good query plan. It tries to then not spend too much time on it. And then it tries to support the extensible aspects of Postgres, right? We heard about timescale DB earlier. There's PG vector. There's many ways how Postgres needs to understand these extensible aspects whilst planning a query. What Postgres Planner doesn't do is it won't find all the possible query plans, especially if you have lots of joins. It will not change a plan when the expectations change. I think this is the most surprising thing to some people that might use some other commercial databases, is Postgres is kind of simplistic. Like it will keep doing the stupid plan essentially without thinking about what it's done. And it won't track to execution performance essentially. Now, what's my iterative loop when I'm doing performance debugging? So I started with a slow query on the top left, and I realized it's slow. And in this case, I've realized it's a database, right? So this is the very first thing. You need to know if it's actually a database or not. Let's assume for now it is. And then I want to do a benchmark. So I run explain analyze. I form a thesis on what I want to change. And then I try out the change. And if it's actually made it faster, I figure out a way to make that change permanent, right? So really my goal here is to give you a few ideas on how to do this part better, which is about forming a thesis on what to change, because this is the most challenging part, like as a novice with Postgres, to understand what you might be able to do to make the query perform better, or what the problem might be, why it's slow. And then, sometimes the change in production might look different than the one you're testing with, essentially. All right, how to interpret explain, analyze buffers. Okay, so explain without analyze, just the raw explain command, will tell you what the planner, which plan the planner has chosen, but it doesn't actually run the query. So the benefit is it's really fast. Even if you have a really inefficient query, just putting explain in front of it is just going to give you that plan. And so you can test different things, like different assumptions with that pretty quickly. Explain analyze tells you the plan that was chosen plus the actual runtime statistics of that plan when it was executed. And then buffers adds in I/O statistics, which tells you how long did it take to read the data, how many gigabytes of data were loaded, how many pages. So that's actually very important if you're trying to understand, is I/O my problem or is it maybe something else? Now explain, just without any options, looks like this. In this example, we have a parallel query, does a sequential scan, gets the data together essentially and returns it. Very simple, very inefficient probably. We see something here which is called cost, which I think I have something more in the next slide. But essentially, the important thing to understand is this is hierarchical. So you see at the top node, you see this cost value of 97,000. That doesn't mean that the top one is that expensive. It means that it and all its children are that expensive, or estimated to be that expensive. And so we need to essentially do some math here by subtracting, the bottom number from the top number to know what the self cost is of the parent. Now, explain analyze will give us information like it actually ran for 307 milliseconds. It removed this many rows by filtering this data. It actually launched 2 parallel workers, like all that information. And we also do have the actual time here on the right side, a little bit cut off. Same rule applies, right? You need to essentially subtract the children from the parent to really get the value of each individual node. There are tools out there that can visualize this for you. If you don't know one, just search for it. There's a wiki page. Makes it slightly easier to read and do the self-cost logic. Now, if we add buffers, we also get buffers and I/O timing here. Buffers essentially tells us how many buffers were loaded if it's buffers read, or how many buffers were essentially used if it's buffers hit. Now, a buffer is an 8 kilobyte page usually, so you need to multiply this by 8 kilobytes to get to the gigabyte number. And then the thing to be aware of here is that this can actually be very different. I'll kind of like read to you the numbers since they're hard to read. So in this case, in the top example, we have shared hit equals 11. In the bottom example, we have shared hit equals 50,000. And the example here, this is from a blog post that Nikolai posted a couple of years ago, is that this is a bloated table, right? So you have the exact same amount of data. The table is just really inefficient, essentially. There's lots of unnecessary data being loaded. And so you get the same result, but you're essentially spending a lot more I/O doing so. The other thing to be aware of is, and this is something I've only learned, I want to say like 3 years ago, 4 years ago, is the hit counter can double count. So if you have a loop, for example, Postgres might read the same page twice in a query, and it will count up that hit counter. And so you got to be really careful. Like this essentially says, it's in the cache, right? I found the data to be loaded in the cache. But you really need to interpret that correctly and be aware this might be a huge number, but it doesn't mean that Postgres necessarily loaded that much data. Also, explain analyze itself has overhead. So if you're running explain analyze, it's going to be really fast if you have a few rows that you're working with. But if you do a select count star on a big table, explain analyze can actually be twice as slow as the actual query execution. There's various ways to make it faster, but just be aware that you should run the query itself essentially to really verify the performance. All right, cost estimation and selectivity. Cost estimation is really what drives the Postgres explainer behavior, right? Like it's that number that we saw earlier in the explain plan. It's essentially, there's a startup cost, which is the cost to kind of get the first row or the 0th row, so to say, and the total cost, which is, get all the rows. If you have a sequential scan, the total cost is essentially how expensive it is to get all the rows in the table. You also, Postgres estimates how many rows there are going to be returned and how wide those rows are, like how many bytes they have. But what is cost, really? It's kind of confusing, right? What does that mean? It's not really a unit that means anything. It's really more of a currency that Postgres uses when it does its cost-based search, right? So the cost of a sequential scan fetching one page is 1, but that's about the main thing that you can really say about cost. And so just be aware that higher cost is more expensive, essentially. Which, if you want to know, you can look at the Postgres source coming to, hey, here's some C code. You can see that, in the cost sequential scan function in cost size.c, you can see a very simple logic which says for the current table space times what's the sequential page cost setting times the number of pages, and that's essentially the total cost to read the table in a sequential scan, right? This logic is in a sense very simple, like simple math. What's the cost of an index scan? We can do cost index in also want to say cost size.c. And then there is an index access method specific cost estimation function. So for example, a PG vector has special index types like IVF flat and such. And so those index types will have different cost estimates than a regular B-tree index. In PT cost estimate, we actually find something really important, which is what's called selectivity, specifically the clause list selectivity function. This essentially says, what's the cost of reading this index? It depends on how selective your where condition is. Like if you're reading, if you're matching essentially everything in the index, you're going to read a lot of index pages. If you're matching a very small number, you're going to read very little. And so this is really one of the most important things to understand is this is one of the hard parts about when Postgres gets things wrong. It's oftentimes related to selectivity. Now, selectivity, to be clear again, means how many rows does Postgres think it will need to read, or like how effective is the filter, for example. And so low selectivity would mean you're reading a lot, essentially. Although the number is kind of confusing because it's between 0 and 1. 1 means you read everything. So sometimes hard with the low and high. But there's a function here. You can read how it does this stuff. The one thing to call out here is that Postgres does something kind of naive here, and we'll get back to that in a second, but there's a thing called extended statistics, and that really makes a big difference in how Postgres does these selectivity estimations. Now, to illustrate this a bit more clearly, right? So here we have this filter, my table at user ID equals 1, 2, 3. Selectivity essentially says, how effective is this filter? That's essentially resulting in the number of rows being returned. The most typical case that I've seen where selectivity estimates are bad is because rows are not actually independent. think we had earlier the example of, I want to say, region and break in your talk. And that's probably an example of where clauses are not independent, right? Because the break is in a given region. And so that means that, once you know the break, you probably know the region. And so adding the region filter to query wouldn't make it more specific, right? And so that's very important to understand because Postgres doesn't know that. Postgres would assume they're independent by default. And so slightly less good example here than that. But the benefit is you can tell Postgres to use create statistics to essentially gather more information and to sample the table to know about these relationships. And so the way you can do this, another example here would be zip codes and states. Except for, I think, very few exceptions, a zip code is in a given state. And so if you're querying for a zip code and a state, this would essentially tell Postgres that there's a functional dependency, or well, it would measure the data to be able to determine that zip code and state have a relationship with each other. And so if you query one and the other, you probably don't reduce selectivity essentially or increase selectivity by having both of these filters. Now, kind of switching gears a little bit, join estimates are actually a lot more complicated, right? So this is the easy stuff in a sense. So if you have a query that behaves this way, you do create statistics, you do analyze, you rerun your query maybe chooses a better plan, behaves better. Like this is easy by comparison. This is the hard part. So Postgres, when it joins two tables together, also has a row estimate, right? Because it tries to understand how many resulting rows are there. And we definitely won't get into the details of that today just because there's not enough time, but just be aware that this is complicated. There's most common value lists that are being used. This takes a lot of time to get right, and sometimes the answer is there is no good way to get a good estimate there. And you can, well, sometimes you can raise the column statistics target to get more samples, and then the plans do get better. Let's talk about join order a little bit, because that's one of the other things that I want to say in the last 5 years actually understood how that worked. So when we have the planner finding, so what the planner does when it plans is it goes through essentially all the tables being referenced, and it essentially makes two different plans, like subplans you could say, subpaths, for each of the tables involved. First of all, it tries to find the cheapest path, meaning the best index, for example. And then it also tries to say what's the best like kind of scan method if the table is being parameterized. We'll get back to that in a second. Now with that data, Postgres will, for example, say here we have a query select star from A, join B, join C. Let's suppose for a moment here we don't have any condition, like any filter on A, so we'll just do a sequential scan. B, we have an index, let's assume, so B tree X, right? So we do B.X equals 1, so we can use that index. And then C, the same thing, we have an index on the Y column, so we can use an index there. So this happens early in planning. Now, then Postgres tries to understand how does that data get joined together, right? How does Postgres actually, kind of come up with the actual execution order? And so one way of doing this could be saying, we do a sequential scan on A first, we do the index scan on B, and then we join them together with nested loop join. And then we also, have the index scan on C happening, and that gets joined together with the result of that outer nested loop through another nested loop, which results in a join order of A, B, C. The same thing can happen the other way around. So we can say A and C go first. That results in A, C essentially being joined, and A, C, B being joined. This sounds a little bit academic, right? Like, why do we care about this? But the plans perform very differently with different join orders, and you get very different performance, essentially, and like scan methods, for example. So you can represent join order like that with these parentheses, essentially. Joining lots of tables is also a problem because it's essentially a factorial problem, and the Postgres will stop doing the optimal search after 12 tables by default and use what's called the genetic query optimizer. That sounds fancy, but it's actually not that good. And so usually if you have lots of joins, you will see bad query plans, is the gist of it, and there's settings you can change to essentially get better plans. And so yeah, we essentially have three essential choices here, right? We have a certain way of scanning the table, we have a join order, and we have a join method. You can analyze this. This is a prototype I built a couple of years ago, well, a year ago, on how to analyze this with a bunch of explain plans. Like if you look at an explain plan, you can essentially come up with a join order. And then I don't think I have this in this presentation here, but you can use pg plan to force a join order. So if you want to understand, how would the query perform, there's actually a way to force it. The other thing I want to explain to you is a little bit of a complicated concept. last complicated thing, I think, in this presentation here. So suppose here for a moment we have a table T1 and a table T2, and we're joining them together. And we're filtering on the first table. Now, one way this could be implemented is you can do a hash join, right? And you can say, let's get the data for T2 in this case, where there's no filter. And then let's also get the data for T1 because we have that condition there. Now, this is one way of doing this, right? This would be like, looks good, hash join is good. But really what's inefficient here is we have the sequential scan. Now, the alternative plan that we could see here is that Postgres could use a parameterized index scan. Now, what that means is if you look at that index condition, it says T1 ID equals T1 underscore ID, that's essentially on the T2 table, the reference, is essentially compared with the output of the other scan. So it means we first scan this table, and then we scan the next table, which let's use an index in this case. The reason it's called parameterized because we're essentially having a parameter from the other table in here. You'll often see this, typical Rails apps will have a lot of these, right? Like that's a very typical thing in a Rails application. Very different plans, right? The thing you can do here, actually, the thing to know about this can only happen in one of the two tables. So you can't have the parameters on both, essentially, because you need to get one table's data first. All right, I'll leave you with 5 actionable tips, and then we can do the break. First of all, if explain shows you a sequential scan, you may want to look at your indexes. Not always, right? Sometimes there's definitely cases where the plan is bad, but indexing is a very different topic, like which indexes to create, than what we just talked about, which is more how does the planner work, how do these decisions get made. And I did a webinar a while ago on indexing and wrote a bunch of blog posts. Happy to give you some references if you want to know more about how to find the right index. Really try to use that buffers option because it does give you a lot more data and it does help you understand, is this an I/O problem or something else? If the estimates are off and you get a bad plan and you have functional dependencies, really look at create statistics. Postgres really should be doing this by default, but it doesn't because sometimes there is overhead with this. But I would say for most typical applications, if you have customer ID, organization ID, like all these ID columns, and you're including multiple of them in a query, then you'll benefit from create statistics. If you can, and especially in a multi-tenant application like many Rails applications are, it does actually help Postgres to add additional clauses. So Rails wouldn't do this by default. So Rails, if you had the active record ORM generate a query, it would just usually you have the filter clause on one table, join the other table. And if you had a customer ID on all your tables, you could essentially have where table1.customer ID equals this, where table2.customer ID equals the same value. This seems unnecessary, but it will actually oftentimes improve performance because it doesn't have to use a parameterized index scan, right? So there's essentially that trade-off that Postgres, if it doesn't know this information, will have to do extra work. And I've seen performance be improved by essentially adding extra where clauses. And last, and this is why I wanted to give this talk here, is I think query optimization is a team effort. Many of you probably have other members on the team that actually work with Postgres more than you do. And oftentimes they end up being overloaded with things that they need to take care of. And I do really think that, especially in larger organizations, we need to essentially teach everybody a little bit, at least, of how this stuff works, so that you know when you can fix things yourself, what to try, and when to maybe involve somebody else who might have spent a lot more time on this, essentially. And with that, if you want to find me on the internet, I'm in the Fediverse. I'm also still on X, although probably not long. And you can email me at lucas@pganalyze.com. I also host a weekly video series called 5 Minutes of Postgres on YouTube. And there's a longer version of this if you found this interesting. I gave a webinar in June, which essentially was an hour-long version of a lot more details on this. So, thank you, everyone. And I think we'll skip Q&A and just do a break. All right, a couple of questions? Okay, sure, sounds good. Just want to make sure. All right, and I'll repeat the questions for the recording, just
Create statistics, is that a one-time cost or is that an ongoing cost once you get it set up?
Okay, so the question was, I should not be in front of the camera. Wow, that's great of you. All right, so the question was, create statistics, is that a one-time cost or an ongoing cost? So essentially what it does is the create statistics command itself tells Postgres each time it does analyze, it collects more data. And then each time you have a query running, it will have to look at that data also, right? that said, the data is very small. Like functional dependency statistics is essentially one number like next to another number for two columns. So it's like, you know, like less than 100 bytes essentially of data usually, or less than a kilobyte of data. So I would say, yeah, like the cost is ongoing, but the cost is very tiny unless you have very large wide columns essentially, or include lots of columns. Other questions?
Okay, can I ask a stupid one?
Please.
This all kind of lives outside of Active Record, right?
Yeah, so the question was, this lives all outside of Active Record. And the answer is yes, it does, right? Follow-up question, why? I mean, in a sense, like it does and it doesn't, right? There is clearly a relationship between what the application generates and what the database has to do. I mean, N+1 is a good example. So if you solve the N+1 problem by making one bigger query, suddenly you have a slow query optimization problem, right? So it's kind of a trade-off. It's an interesting question. Like sometimes, you know, in the community, people come and say, well, why doesn't the planning, like especially when plans go bad, right? People have more controls over plans. And then they're like, well, why can't I just send the query plan to the database server, right? Why couldn't my Rails application generate the query plan and just tell the database what to do? And that's a good question. I think the answer that the community usually has given, and Postgres is kind of notorious for not having query plan hints, for example, at least not built in, is that essentially that's what people want, right? It's like they want the database to figure out how to execute the query, right? So if you want to write the application side logic to combine data together, you should probably use a document store or something, right? Where you essentially have to do that work on the client side. But the relational database really does that work for you. And so that's why we have that model, I would say. And so yeah, oftentimes, if it is a slow query problem, it's definitely a Postgres problem, not a Rails problem. One last question, maybe? All right, one more from you.
Are there any things that you would see in the explain or analyze output that would be very different, obvious, if you have a different types of cardinality of your data? Like if your table has like 2 or 3 different values for a particular column versus a column that has thousands or hundreds of thousands of different particular values.
So the question was, if you looked at an explain plan, would the explain plan look very different if you had a table with like lots of distinct values essentially versus very few distinct values? It's a good question. It will definitely lead to different behavior, right? Like index usage, for example, would be defined by how many distinct values there are and how like selectivity is of the particular clause. I think in the plan itself, you kind of have to look for it. I mean, the rows estimate in a sense can represent that, right? But it will be impacted by any work conditions you have. So I think this is something where it does help to kind of go beyond the explain plan and look at like PG stats, for example, is a built-in statistics view, right? So if you want to know, like we talked about extended statistics for a moment, that information, like the create statistics data that lives in PG stats ext, I think. And so you can just query that view and see which numbers Postgres collected essentially as part of analyze. So that's how I would go with that. All right, well, if you have more questions, you want to talk about this more, feel free to catch me in a break. Otherwise, enjoy beverages and other things.
Going into a 20-minute break now. So let's chat over there. And let's try more of that amazing salad. So the open mic is starting in a minute. So folks, think about your short announcements, questions, ideas. Maybe you're looking for a friend. Maybe a job. Maybe you're looking for a mentor, or maybe you're looking for a buddy in open source who's maybe more into open source and you want to get into open source and you want to really kind of connect with somebody. Yeah. So this is open mic.
What's the name of the YouTube channel this gets posted to?
It's going to be a freshly minted YouTube channel. No. This is going to be, yeah, so this is the first time we're recording this. My inclination would be to post it to Evil Martians channel. So yeah, we have a channel, first of all, and we can post there. Yeah, let's do that. Good idea. But also, after, to be honest, I forgot it last time, but after this, I will ask all the speakers to upload their presentations to Luma. I mean, just post links to Luma so that people can check out the presentations. And then, yeah, the video, I will also post the link when it's available. And I will also remind you about, I will also post the link to the survey we have. So to remind you, we have a giveaway of 2 amazing Rails books. So Andrew Atkinson and Vladimir Dementiev. And we'll randomly select from people who filled out the survey. And I've already checked that we have a bunch of responses, which is amazing. Thank you so much to everyone who did this. So this is the open mic, and this is for you.
Me? Okay, cool. I'm only coming because you kept staring at me.
Yeah, just tell us about yourself or something. Yeah.
Or something.
Hello, everyone. Hello. What's going on? What's going on? My name is Jeremiah Larivo. I'm from Jersey. Anyone from the East Coast? Woo! Woo! Where you from? Where you from?
DC area.
DC area. I love DC. One of my favorite cities. I only came up because I was being stared at. So I don't really have much to say, but I can give a quick background about me. I am new to engineering, new to programming. I did a boot camp. Very exciting, very exciting. I did App Academy, so they focused at the time in Ruby. So I'm working in Rails 7. I love it so much. I love it so much. Background. My background is in operations and in management, some leadership. I know how to start a business, run it, market it, sell a product. And I was like, I want to be one of the people who build that product and then eventually make money. Yeah, I always wanted to build that product. And Rails has given me the opportunity to build great projects and do little fun things. I've been doing freelance work just to pay the bills. Shout out bills. And last thing I did is build just a small e-commerce website for a local business. Well, they're local to New Jersey. And that's been fun, but it's really been forcing me to expand my skills and think outside the box, use Ruby docs a lot. And I don't know, I've been like really trying to be the best engineer. So I don't know what things I'm looking for. Obviously a job, shout out anybody hiring. But maybe a mentor, someone who can help me clean up my code, how to think through things properly. Yeah, be a better engineer. So that's about me.
Look at this. Amazing. I'm all okay. Who's next?
Hi. So, quick question. So, like, my background is I had a very toxic relationship with web dev. I know. So, like, for reference, I've been programming for like 7 years. And for 4 of those years, I had a very shitty old like Dell laptop with a touchscreen, like, the foldable ones. And for that thing, it had a very bad processor and graphics card. So I couldn't do AI, I couldn't do inference stuff, I couldn't do any like CAD or stuff. So the only stuff that could run was Node. So that's why I did web dev. And nowadays I do hardware stuff. I speak clocks, I speak Verilog and C in assembly. So my question for you is, I've never touched Rails and I just got here. So like from a pragmatic standpoint, I hate React. I love Svelte though. Svelte good. What's my other hot takes? Tailwind good. Bootstrap bad. Okay, I offended someone probably. Material UI, the styling is bad. So like if you like the components, Chatien is nice, great, love Chatien. No one? No Chatien? No? Check it out. that and Eternity. Those are like if you're trying to build a startup, that's what those are the components that are abstraction layers on top of Tailwind that make it functional and look good.
Post.
A what?
Post to Luma.
Post to Luma? I don't know how to do that, but
She'll tell you.
like if I were to hypothetically switch over to Rails from Svelte, why should I leave Svelte and why should I stay with Svelte? This is not me attacking Rails. This is me seeking the truth.
Folks, you know, I know the answer to this, right? Right. So first of all, you want to choose Rails. It sounds silly to answer while hosting this, but you want to choose Rails seriously when you're building a web application and you want a framework for the web application. This is Rails, the most productive, the framework that is making you the most productive developer. This is Rails. Then you can choose for the front end what you want. You can start with Rails full stack, Hotwire, Vue component, maintainer of Vue component. You can use Svelte. It's not a problem. And nowadays we have even more kind of efficient tooling for integrating Rails with Svelte, React, and Vue. And it's called Inertia.js. And you can go to evilmartians.com and to /blog and read all about that. And we have documentation and for Inertia. It's like a central stack glue between Rails and front-end frameworks that doesn't require you to build API. Like, it's simpler than API. So, yeah, great question.
Yeah.
Any other takers to answer? Okay. Any other? Somebody else wanted to. Okay.
Hello, everyone. My name is Chris. I work at a startup called Binti. Irina, you were just asking about startups using Rails. Binti is one of them. We are on a mission to make sure every child in the world has a loving family. And we're doing that by reinventing foster care with technology. And so if that sounds like something that's interesting to you, our stack is Rails on the back end, React on the front end, GraphQL API, Postgres, GCP, all that kind of normal stuff. Yeah, if that sounds like something interesting to you, we're going to have a couple of roles open pretty soon. We have an application security engineer position open right now. If any of that sounds cool to you, please find me later. I can make sure you're in our system for when those postings go up. Yeah.
Awesome. Anybody else? Okay. That's the open mic. Are you sure? No? No? Okay. I will be staring at somebody until this person comes up. Okay. We continue. So the next open mic is going to be at the next meetup, which you remember. You got to register to. I will send you all emails, email invitations to that, of course. Yeah. But now I'm super happy that we continue, and Yang will talk to us about something. Dokku. Okay, quick question. Who knows about Heroku? Okay, who knows about Dokku?
Oh, okay, that's cool.
Hi, my name is Yang Chung, and long-time lurker of Ruby meetups, first-time speaker. So we'll see how it goes. All right, cool. So we continue. So like, I was trying to pick a title, and then it's like, okay, it's gonna be like a Dokku, and it's similar to Heroku, and how we're gonna like create a title. It's like, okay, like I'm just gonna say Dokku your way to Heroku. Like it just rhymes. All right, cool. I feel like got them like narcissistic to talk about me. But there's a reason I'm talking about me. But anyways, so I started my career as a network engineer, and then tried to do a startup, failed, and became a PM. And then I had another opportunity to do a startup, which also failed. So then at that time, when I did a second startup, I was a full-time founding engineer. So I decided to continue being an engineer. So, and that's when I used Ruby and Rails at the time. Anyway, so some of the experiences I had, I pretty much studied my career at UUNet. I don't know if anyone's heard of it. Oh yeah, I know how old you are. All right, cool. And then moved to Silicon Valley. I worked at Caspian Networks. And then there's another company I worked at. Shout out to a few colleagues over there. And then I worked at Pebble. I'm wearing a shirt. So I mentioned Pebble because Pebble, actually, we use Heroku as our, server. Because there are only like 2 of us doing all the marketing website, e-commerce, all the back office, and dealing with all the Kickstarter backers. I don't know if you heard of okay, so maybe some people don't know that you have a Pebble. We are the first ones to make the most, raise the most money on Kickstarter. The first one, we did a $10 million. Second one, we did a $20 million. But we ended up closing our doors, and the Fitbit bought our IP and some hired some engineers. Anyway, so we did a lot of we used Heroku was great because we didn't have any dedicated DevOps person. So just 2 of us doing all the work and just keep push Heroku mastered, and then it's out in the public. Enjoy Technology, another place I worked at, and then Charma was bought by another company, and now I'm a staff engineer at Clockwise. Anyway, oh my gosh, okay, I'm supposed to stop there, but say you're at a really cool conference, RailsConf or a Rails World, and there was personal projects came up, side projects came up, and it's you wanted to show off your personal projects, and then you see this, right? Panic, right? And then you search for, you look at the log, and you see this message. It's what is this, right? And then you realize, oh, it's maximum number of rows reached because you're using hobby version. And just actually, I just checked it out. So they don't have the row limits anymore. They just charge you by hour. So anyway, anger, right? And then so I have 3 pages worth of all the side projects and personal projects. They're pretty much abandoned. So then, sweating because a lot of those things could be having those errors. Then I found Dokku, trying to find a way to see how I can have it easily deploy your projects without having to nickel and diming, having to pay a lot of stuff. So, and you can also, so this one, so you just need to have your own server. It could be VPS or dedicated server, and then you can do it on the DigitalOcean, whatever. And then, yeah, and then just after simple setup, you can just do git push remote, git remote URL, and then your main branch. So that's smart. I mean, I don't know if you see a pattern in this slide deck. It's a lot of memes there. Anyway, why Dokku? Okay, so I touched a lot about this already, but it's after Heroku was bought by Salesforce, I feel like they're nickel and diming a lot of casual users. And so with this, you have a total control over everything you do. And then you could also do, technically, I'm actually doing this too, multiple Rails apps on a single server. You could do that too, because Dokku, what it does is that it containerizes everything. And then there's pros and cons of it. So pros would be if you have a simple project, you can do multiple Rails apps on a single server. And yeah, deploy to production with ease like this. And then the Dokku has a very healthy and active open source development. And while I was actually researching this, I found out that also the Dokku was first started by a guy named Jeff Lindsay. He was sort of like, he is related to a Hacker Dojo where I was like a big early member of. He and Dave Weekly started like Super Happy DevOps. I don't know if anyone's heard of Super Happy DevOps. Yeah. So from that, they did a Hacker Dojo, and then anyway, so like if you go to like Dokku's open source, the GitHub page, at the end you will say the copyright by MIT, copyright by Jeff Lindsay. Anyway, sorry. Yes, kept. All right, but because of you control everything, that means also you're responsible for everything. So anything you do, there's like no, well, there's a, okay, so like there's a, like, there's an easy way to add stuff to it through plugins, but you're also limited by what plugins are available. But there's something you want, but they don't have it available. You could totally like build your own plugin and publish it. So like, because it's all containerized, right? So that everything, all the Postgres server and then the Redis server has to be in that one container. So if you do like this Dokku on a single server, then you get everything, you have everything on it. But if you have multiple apps on a single server, then it's pretty inefficient way to do it. I think there should be a way to connect to like remote database server, whatever, but I haven't actually looked into it. Like say limited plugins available, but I think that I looked in the list of plugins and they're actually quite plenty. Anything you need, Postgres, Redis, Elasticsearch, whatever. Yeah, so with the great power comes with great responsibility. Simple steps, get your server, Dokku, SSH, create an app, blah, blah, blah. All right, so this is how you install Dokku. And then you just need to add your public SSH key. And then these are how you install the plugins. And then go from there. So with that, we're going to do the live demo. After praying to a demo god. All right. Okay. So for the interest of time, I already installed the Dokku and plugins. So we're going to go from like creating apps. Oh, cool. Awesome. Okay, here you go. Okay, so I already have SSH set up. So you have to do is, well, let me show you what the heck it is. So I have a SSH where I have a Dokku demo. So having this SSH config allows you to easily just say like host name and then like SSH into it. So I'm going to do, okay.
The question, do you guys hear that?
They could sit closer.
Do you think it kind of picks up for the recording?
Oh.
That's what I'm kind of a little bit worried about.
Oh, okay.
Can you use sign language? Just hold it.
Oh, okay. Thank you, Rina. All right. So this is my server. And so you can do, so first like, well, I can copy and paste it, but apps. So I'm going to just call it blog. And just do this because it's much faster doing this way. Just go copy and paste. Oh, and before I do it, okay, hold on. Let me just show this. So I'm gonna go to blog. I just want to show, like, as a magician, like right now, it's like nothing's there. Okay. All right. So, and then you want to create, so this is how you create Postgres, and then you name the table, right? So block production. And what you want to do is you want to link to your app. Then you create Redis. Because right now it's like I'm not actually using Redis, but I just like that just to show how what it looks like. Right? So cool. Now, you want to add the domain because I want to show like how to like they make it really easy to also add the let's encrypt. So I'm going to show you that too. So you want to add domain to it. Let's see. Like that. So Dokku domains add your app and the name, and then if you do so when you when you create Dokku, it uses a global domain name dokku.me, and you want to remove that before you do let's encrypt. Domains. So it has like blog.dokku-demo. You want to remove that because like when you enable let's encrypt, it will complain about it. So remove that one. So we only have blog.listurio.com. That's another personal project I have, but never mind that. And so I'm going to go to first you set the email, then enable the app for let's encrypt. Go. Cool. And then you can also set the auto renew on that so that you don't have to worry about renewing it, and then add a cron job for it. All right, cool. You're all set. And then just like the Heroku, you want to set the resource to web 1. And let's see. Oh, that's all done. So I'm going to exit from it. So that's all you have to do to set up your app on the Dokku on the remote server. I'm going to exit from it. And then, so I already have this blog site, and I can do server. So that's bx is a bundle exec. I mean, this is a really simple, like, oh, hold on. Need to make sure that the Postgres is running.
Somebody didn't pray.
I know, somebody didn't pray, that's right. So the Postgres wasn't running. So anyway, so here's a little blog. All right, so I'm gonna get out of that one. Okay. Here, so I already have, actually I already have the Git set up here too. You can do Git. Here, so the username is always Dokku. And then I have a @Dokku-2 because that's how I set up the SSH config, and then colon, and then your app name, right? And then, so here's the magic. So git push go. So I mean, it looks just like Heroku when you like deploy it to Heroku. Yeah, that's exactly what you see too. So it detects what app it is, it installs all the gems. And then, so, oh, I should show proc file too. But anyway, so in the proc file, actually, so just like the Heroku, you want to have a proc file. And you can have a release one where it's like, okay, so after release is done, do db migrate. Let's see. Okay, so installing Rails takes some time, but anyway, it'll be done soon. But meanwhile, do you have any questions? Maybe we can answer questions while this is going.
Where do like load balancers and stuff come into play with Dokku?
No idea. Because like, I mean, so it fits my needs because I'm actually hosting just my personal apps, personal projects. So because like, I mean, you don't want to, okay, so like, I don't think that a lot of people are using Dokku for production. And I think that the Dokku will be, and I've seen some people actually using Dokku for staging servers. But for me, it's like, oh, these are my personal projects. And I mean, at this point of all my personal projects, like 3 pages worth of personal projects, they're all looking for a product market fit. So you don't need to have like really like load balancing and whatever. Like that's almost like premature like optimization at this point. Because I just wanted to see like people can find my product useful, and then I can think about maybe moving to like AWS, whatever. But like Dokku, works for my. Anyway, so this is done. So gonna go there. There you go. Yeah, take something. Hold on. So I want to make sure that it works. Okay, so this is actually like this is what backend engineers do. I'm like backend engineer. Like we don't want to touch like front end stuff. So this is actually using Bootstrap. Somebody said they hate Bootstrap, but anyways, it works for backend engineers. Anyway, any questions? Oh, that's it for me. And then let me see the last one. That's it. All right, cool. Did that one. Okay, so thank you. So that's my. So if you want to chat with me, whatever, so like yangdom@gmail.com. That's my email address. But my GitHub and Twitter or X handle is yangdoman. So you can just like reach out to me too. But yeah, thank you. Any questions? All right, cool. All right, thanks.
If somebody else has live demo. Okay, next up is Cameron. Cameron, the maintainer of Vue Component.
One of
the. And yeah, Cameron is the first person to make a repeat appearance as a speaker, right?
That's true.
Yes, at this meetup. So he gave a presentation before on the alternative front-end stack, like on how we could build front-end in Ruby and transpile it. It was super cool. But today I'm going to hear about something cool. We've already seen some C code today. So yeah, let's do more.
Oh, it works. Awesome. Hello, everybody. Thanks for bearing with the talks until mine came up. I noticed nobody's asleep. That's a good thing. So we're going to write a C extension today. There was some C in a previous talk, which I wasn't expecting. So you've already seen some C. Hopefully that makes it a little less scary than it otherwise would be. Yep, I'm Cameron Dutro, or for GitHub. I live just a couple miles north of San Francisco in Solano County. And actually, you know what? I'm going to see if I can get my slides to also show up, the next one to show up, because I did not practice this very much. And it would be nice to be able to see my talks, the next slide coming up. Is that possible? Sometimes it just works. Sometimes it doesn't.
No, it's not citizens.
Oh, yeah, you got to mirror the display. That makes sense. There we go. Yes, excellent. Okay, cool. Okay, so what are C extensions? So as you may know, Ruby, or MRI, Matz's Ruby implementation, is written in C. And you can extend Ruby by writing extensions in C as well. An extension is really just a little C program that you can then use as if it were written in Ruby from Ruby. And one nice thing about extensions is they're kind of a first-class citizen in the ecosystem. And so Ruby gems will automatically compile these extensions for you when you install gems, etc. So why would you want to do this? Why would you not just want to write Ruby all the time? I mean, I know I normally would. Well, there's a couple reasons. One of the big ones is performance. Writing code in C is generally more performant than code in Ruby. That's not always true, especially with the stuff being done with YJIT now. But that can be a valid reason to write a native extension in C is performance. You might want to wrap a native library in a Ruby embrace so it can be used more effectively or idiomatically from Ruby. So examples of that might be ImageMagick or SQLite, libxml. So for example, Nokogiri is just a big C extension wrapping libxml. You also might want to have low-level access to hardware. If you're trying to, for example, program a Raspberry Pi, or you want to communicate over some GPIO pins, you might want to use C for that. Or, as we'll see in this example, you can also write one just for fun, because what we're going to do is really stupid. So our goal for today is to create a gem with a native extension, and this extension lets you change an object's class at runtime. Now, I should have heard a shiver go through the audience, because that's really, really a terrible idea. And I'll tell you sort of why I thought that was a semi-good idea when I first made this gem. Here's the basic API, and the code you can access. It's on GitHub, cameratron/transfigure. So we have two classes. We make a new instance of foo, and then we call a method called transfigure into exclamation point or bang, pass in another class, and that will then transform that object from an instance of type foo into an instance of type bar. Okay, as I mentioned before, it's really a terrible idea. And as we'll see, Ruby's C code actually actively tries to prevent you from doing this. We'll have to try to get around that, though. Okay, so yeah, so what somebody asked me, I was sort of pitching, I don't know, I'm mentioning that I was going to be speaking today to a new friend that I just met when I walked in the door today. And his question was, why? And I realized that I didn't have any explanation for this in the talk, and so I sat there trying to add a couple of slides to try and explain why you'd want to do this. So this is going to be a half-baked explanation, just get comfortable with that idea. So Ruby objects are always of one type. We can't change the type of an object at runtime, which of course makes sense. But what that means is also it's impossible to treat a class as an instance of its supertype. And what that means is that if I have a class hierarchy like this, I have grandparents, or a grandparent class, and a parent and a child class, and those are inherited up the chain there. If I want to grab the foo method, then call it super method, I can do that, of course, with super, the super keyword. And I'm deliberately not doing that here because of reasons that will become obvious hopefully in a second. If I say child.new.foo, though, any idea what will happen here if I try to run this code? Anybody at all? It's okay, I didn't know the answer to this either. The answer is that you get a giant system stack error. And this happens because if I try to grab, like in child, my def foo, that grabs method foo and calls it super method. But when that goes up the chain to parent's foo method, we do the same thing. We try to grab the method foo, but because our class is of type child, we're simply grabbing ourself. We're grabbing the foo method defined on child and then going back up the chain in an infinite loop. So we grab, like child grabs parent's foo, but then parent can't grab grandparent's foo because child, the class is still of type child. And this is in direct sort of contrast to a language like Java, which does let you do things like this. So in Java, I can refer, like super is an object or a reference to an object that looks like it's an instance of the super type. So I can say super.foo all over the place and it works as you'd expect. So what I kind of would like to be able to do is something like this in Ruby where I can say, okay, like just treat this object as if it were an instance of the super type for a brief period of time. So I can call some methods on it as if it were an instance of that type instead of the base type. Okay, so with that very flimsy reasoning aside, let's try to write a C extension that does this. So here's our directory structure, and this looks a lot like a regular gem. You have a rake file, you have a lib directory, a spec directory, you have a gem spec file, all seems pretty normal. The special part is this ext directory, and this is where our C code will live. There's a couple of, one subfolder in here called transfigure, which is the name of the extension, and then a file called xtconf. This thing will help us create a make file that will then be used to build the C code, and then the C code itself in transfigure.c. So our gem file is really simple. We're just, or .gem spec rather. This is, or I guess it's the gem file, but with a gem spec reference in here. You get it. We're going to add a special gem in here called rake compiler, and this helps us actually compile our extension. You don't need rake compiler, but I find it really useful to have it in there, so I always add it to my extensions. Here's our xtconf.rb. This thing is, again, responsible for creating a make file. If you're not part of sort of the C world, you might not know what a make file is. A make file is actually like a rake file in that it can run tasks for you, and one of the main tasks that the make files do is compile code for you and then link it into an executable. Ruby has a little helper library called mkmf, which stands for make file. You list the sources you want to compile, and then you say, I want to produce an extension at this directory, or at this path. Okay, so let's write some tests before we actually write some C code. We've got our two classes. I'm doing this in rspec style. We have our object equals foo.new, our first object, and we expect that to be a foo, of course we do. And then we're going to transfigure that into a class of type bar, and then we expect the object to be of type bar. So pretty simple test, I would say. And of course, if we try to run that, it should fail. Let's take a look now at some elements of Ruby's C API that we're going to leverage in our journey to write this extension. So Ruby objects in C are all stored in instances of this thing called a value, all caps value. A value is a struct. A struct is just like a Ruby struct. It's just a little container where you can put a bunch of other data members. So that's where that's what Ruby objects are all stored as values. Nil, so the concept of nil in Ruby, is represented by a value called qnil in the C source code. We define Ruby methods in C via the rbDefine method function. And Ruby methods defined in C receive a value called self as their first argument, sort of like Python, if you've ever written that language. And then one of our last sort of pro tips here is you can grab a reference to Ruby's object class, so the base of the whole object hierarchy, via this special constant called rbcObject. Oh, and then also native extensions like the one we're going to write, there's an initialization function that's sort of automatically called for each extension, and so also that's where we would set up our methods and whatnot. Okay, so armed with that knowledge, we should be able to dive in here and start writing our C code. So the first thing we do is in C, there's this concept of includes. This is kind of like a Ruby require statement. It's just saying I want to make use of things like the value struct, and I have to know how those are defined. And so I include a header file that describes how those structs are laid out in memory. Here's the this will just go a couple of lines in here. This is the function that will eventually be called whenever you call transfigure bang. I'm calling it tf transfigure into bang. We can see that it receives that self value argument as its first argument, and then it also receives the class that we want to turn this object into as its second argument. For now, we're just going to return nil because we haven't figured out how to do this yet. And then in our initialization function, we're going to call this rbDefine method function, which defines the method on the RBC object. We're calling it transfigure into bang. And then we're passing it a reference to our C function. It takes one argument, not including self, and that's it. So this is the very, very sort of skeletal look, or a skeleton of what a C extension might look like. And again, in our case, we're just returning nil here. We're not actually transforming anything. So we can sort of get a feel for how we might do this later. This is just the skeleton of it. So let's give it a try. So we run bundle exec rake compile, that compiles our extension, and then we run spec, which runs our spec. And we'll notice that, of course, it didn't transform anything because, again, it doesn't do anything yet. But we like to do TDD, right? So our mission is to figure out how Ruby keeps track of the class of an object. Then we're going to replace that class with the one we're passed and profit. Hopefully then it works. Okay, so how do we find out how to get an object's class? There's not a lot of easy answers here. I had to just dig through the Ruby source code until I figured out how this works. So having read through it, I came across lines of code that looks like this. I have no idea what this is doing, by the way. I just know that it's got the general shape of the thing I want to do. We have a value object, and we're using this rbasic macro, and then, oh, look at that, arrow class. That looks like it might be the thing we want to look at. So some more code in there. This looks promising. There's something about this that, I mean, I would assume that this is how we would get an objects class. So let's look at how rbasic is defined, that macro. Lo and behold, here's the definition of it. It's something, it says convenient casting macro. It takes an arbitrary Ruby object and returns this struct called an rbasic struct. I don't know what rbasic is. Let's take a look at it. Oh, look, rbasic is the Ruby base struct, apparently, that all objects have in common. That seems like it's probably pretty good. And it only has two members. It has flags and it has class. Okay, so now we're cooking. So that's it, right? We just use the rbasic macro, we cast our value into an rbasic struct, then we grab the class field or assign to it, and we're done, right? Okay, let's give it a try. So here we go, cast ourself into an rbasic macro, we assign the class member to target class. Okay, let's see if this works. Okay, it does not work. We run bundle exec rate compile, and we get this incredibly cryptic C error message that probably doesn't make a lot of sense unless you've worked with C a lot. So what the heck does this mean? The C compiler is essentially just telling us that the field class is marked as constant, so we can't reassign it. So this is what I was saying before, where Ruby actively prevents you from doing exactly what we're trying to do. Let's take a look at this code again. So here's our rbasic struct. Notice that there's a const qualifier in front of it. Yep, not going to work. So we need to hack it a little bit. Also, can I just point out, why is the cable so large? I guess when they made movies in the 90s, like, realism was not one of their top priorities. All right, so here's how structs are. We have to know something about how structs are laid out in memory. So they're laid out sequentially, right? And so accessing fields of a struct is just some math. So if we want to get the memory address, well, I missed it. What happened?
We know what you're doing.
Oh, okay, awesome. Yeah, a little deviousness going on. So the memory address of a struct is just the byte offset. So the address of the start of the struct plus however many bytes offset you want from there. So in this case, we know that flags comes first. So let's pretend that has an address of 0. That means that class, because flags is a 32-bit unsigned long, we know that class must be at address 32. So let's talk about casting in C. So casting changes the type of a variable, and in C, there are like absolutely no guardrails for this. You can cast anything to anything else, and the compiler will say, did you mean to do that? And you're like, yep, and it's like, fine. So that means that something like this works fine. You can have a char star, which is how you define a string in C, a literal string, and I can say, I want to cast that to an int, which makes no sense, but C will let us do that. So since we know that that's possible, we should be able to define our own struct, this time without the const qualifier. So we need to trick the compiler to thinking the class member isn't constant, we'll define our own struct and cast to it. So because memory is laid out the same as the original struct, it should work just fine. So we'll define our own. I have no idea what Ruby align as does. I just copy pasted that. And then I gave it a new name, TF rbasic, for transfigure rbasic. And I stuck 2 flags in here, or 2 members, and I left the const qualifier off of class. And now I could hopefully cast, like we say rbasic itself, and then we cast that to a struct TF rbasic, and then we should be able to set the class on that. Now, there's one extra line of code that I haven't added here that I'm going to add right now. So now that we have that in place, let's try and see what happens. Look at that. Our compile works, and our specs pass. All right, so that's it. Thanks for listening.
And again, don't do it. Okay, yeah, as always, overtime. But our last talk for today is gonna be like a light desert Yeah. After C extensions, infrastructure, Postgres, and time series data. What do you think we can talk about? React. Right. So James, take it away.
All right. All right. This talk is called "Borrowing from React to Build Dynamic Forms with Rails." And my name's James Kerr, and the idea for this talk was born out of my passion project, Tend.cash, which brings clarity to your personal finances. I'm working on the marketing tagline here. And so one of the things you could do is you could add your income sources and your fixed expenses into Tend with a form like this. And it's a lot like a repeating event on a calendar. And so I'm gonna put the mic down and demo this really quick.
All right, I like it.
Okay, so here it is live. This is the interface for Tend, and I'm going to use the form that I'm going to talk about in this talk. So here it is. I'm going to add my income source. And my salary. Okay, and then I get paid on the first. Every month I get paid on the 1st and the 15th, and I expect, you know, I could add an expiration date, which is an optional field, and I expect the AI bubble to pop. Christmas. Okay. So, and this is this form accepts nested fields in Rails, nested attributes. So I could add another payment schedule here, and and they give me $10 for coffee on Friday. So I could. But yeah, one thing to notice about the form is if I change the interval to 2, the word month becomes months. If I change the week, if I change the month to weeks, then this button changes and it's a new dialogue specifically for the weekdays. And then if I select a few of these, it summarizes my selection as the button text. So we're going to build this at the end, and you're going to be surprised how little code we write. And so let's see if it works. I knew it wouldn't work. Okay, so oh, my AI job. So
too many nines.
Too many nines. Yeah. Okay, let me switch to separate display. Okay. All right. Okay, so if there's one thing to take away from this talk, let it be this. It's best just to re-render everything anytime state changes. So another way to put this is, if at all possible, avoid partial updates in your user interfaces. And why? It's just because they're really hard. Partial updates are hard, and these are the reasons why. You have to render things twice. You have to render them in Rails with Ruby first time, then you have to write some JavaScript to your own pluralized method or your own 2-sentence method, and you have duplicate rendering logic, and then you have to manually keep track of which UI depends on which pieces of state and keep them in sync and event listeners, and it's all too hard to manage. And it was even too hard to manage back in 2012 when Facebook hadn't invented React yet. This is a great documentary, by the way, and this line just hit me in the head. Jordan Walk it says he says the most difficult thing to do right in the front end right now is updates. And he goes on to say, it's a huge source of bugs in the Facebook code base. And this is in 2012, right before he created React. He was the creator of React. Okay, but you know what doesn't have any problem with partial updates? server rendered websites, they are unable to do partial updates. So it's really nice. It's a super simple model because every time the state changes for a server rendered website, and in that case, it's either the URL changes or you submit a form, you get an entire new web page every time. The server has to build the whole new page and send it to the client, and everything reloads. And so it's not great for dynamic interactions, but it's an amazingly simple model to keep track in your head. So we want to stay as close to this as we possibly can. And you know what has the same mental model is React. The first time I used React, like 8 years ago, I was really pleased that it's almost the same as a server rendered website. It makes this promise to you as a developer that says, anytime you change the state, I'm going to re-render the whole UI. And it doesn't do this literally, it does it conceptually, like in the implementation, it's very efficient, only change the diff. But conceptually, everything's brand new. Everything's a brand new UI. So React also told me, forced me to identify what state is in the first place in my UI. I had no need to identify it before. And so state is anything that your UI depends on when it's rendering. And so in the React people, they often say this, UI is a function of state. Different state comes in, different UI comes out. So this is the life cycle of a React component. And any screen update follows these 3 phases, is a trigger, a render, and a commit. And so here in this example, some HTML emits an event like on change. In that handler, you call set state, which React gives you, and it's very special. You pass the new state. Anytime you call set state, it's going to trigger a re-render of the whole UI, and it re-renders it into a virtual representation of the new UI, and then it compares that with your current UI and only changes the diff. And it does all this on the client. So it's super fast, and this is why everybody loves React. So we want to mimic this same life cycle in a default Rails app. But first we need to talk about Turbo. Turbo's been around for a while, and I kind of liked it. It was cool. Traditionally, what it would do is it's a little JS library. It comes default with Rails. It comes turned on by default. And it would intercept link clicks and form submissions and perform them in the background with JavaScript. And then it would swap out the body element. So you didn't have to see a blank white screen every time you switched pages. Okay, this was nice. It made it feel a little faster, but it doesn't give us that like really dynamic interactivity that I was showing in the form. Until something amazing happened 7 months ago, and Turbo 8 shipped morphing. Okay, this was me when I saw this video. Okay, so you got to watch this video. Jorge goes through all the pitfalls that I'm talking about of partial updates. He has to keep track of all the state, has to update everything just right, and then he deletes all the code and turns on morphing, and everything works, and it's super simple. So what even is morphing? If a page re-renders itself, so you send a request to the server responds with the same URL, Turbo will detect that, and instead of swapping out the body, it will do a diff of your current HTML and the one that came from the server, and it will only change what's different. And if that's sounding familiar, it's because it's just like React. Okay, so this is the future, I think, of UI development. You render it on the server, and then you have some smart mechanism to update it on the UI, on the front end. We're seeing this with like Elixir and LiveView. They're getting a lot of press. And then React server components, they're kind of like working backwards to get back onto the server. HTMX is another thing that's working on this. And now we've got it with React and Rails and Turbo. Okay, so this is our updated lifecycle of our screen update with Rails now. So HTML triggers an event. We're going to use stimulus to handle it. We're going to submit the form to the backend right away. Any change, submit it. and that's going to make a HTTP request with the form data. That's the equivalent of set state in React. The form data is the state. So that's going to come over to our Rails controllers, and we're going to pick that up in the params object, and that's the state. We're going to initialize our model, and just like what we always do, and render a view, and return the HTML of the new UI. And then Turbo's going to compare our new UI with the old UI and only change the diff. So here we go. Okay, yeah, I might need a stand. Thanks. Okay, so I have this fake version of tend called pretend. And I made a form. I built the form. It's very similar. And right now, this is default Rails new, and form builder. And so I'll say I'm going to add my rent, which is astronomical also. And look, nothing, no interactivity yet. Okay. So now let's go. We need to trigger a re-render. So let's trigger a re-render. We're going to add a new button. Okay, so there it is. I just added another submit button with a value of refresh. So now if we reload, there's the refresh button. And all it's going to do is just submit the form. It's the same button right now. The refresh, create, expense are the same button. They do the same thing. But let's move to the controller. And here's the create action. It's Rails scaffold, nothing new here. And we're going to handle the case where the button comes up as the commit param. So if the button had the value refresh, let's just render the new template again. And a Turbo needs this, 422. Maybe it won't need the 422, but right now it does. Okay, so does this make sense? This is really not much code, 2 lines. So if we're going to re-render the new template. So here we go. Click the button, I refresh. Ooh, and I got the fields that should only be shown if the repeat checkbox is checked. Okay, now let's click that with JavaScript. So I have this controller, a stimulus controller. I'm going to make a method called refresh. This element, I'll attach it to something. So I'll attach it to the form. I'm just going to query for a input with a value of refresh. So that's just going to grab me the button. And what do? Click. Easy. Input. Okay, so let's attach it to the form. Look at basic Rails form. Nothing crazy in here. And we add a data attribute, controller, form, action, change. So anytime this form element receives a change event, we're going to call that refresh method. Okay. This is stimulus. If you don't know stimulus, it's pretty simple, but you can kind of get what this does. Okay, reload. Here we go. Oh, don't have to click the button. So let's just hide this because that doesn't look good. Okay, now we're looking good. Okay, but what's the problem here? Whoops. Here's the problem. Oh, look at the document. It's being swapped out. Everything's being replaced. So you'll see I lose focus. Look, I lose focus, the input, and the scroll position gets reset every time I make a change. And I need my notes for this one. Okay, so, but all you have to do is add these 2 meta tags, turbo refresh method morph, turbo refresh scroll preserve. to the, whoopsies, don't print that, to the application layout. Okay, that's it. And so let's refresh. Now look at that. Look at that. The body document, nothing changing. And I'll show you that it works. It's like 5,000 for a studio. Okay, see the interval changing and the week. The word week gets pluralized. And finally, if we do months, I got all these checkboxes. It summarizes, you know. And this is all just in Ruby in the view, and it should work. All right. Woo. So I mean, I love this. This is so fun. Oh wait, I have to show. Oh no, it's all good. I have to show this too, because this is the diff. I made a pull request to make it dynamic. Look at this, 14 lines of code from a default Rails app to get that really live interactive feel. Like we hardly changed anything. So that's it. My name's my notes. My name's James Kerr. Here's all my links around the internet. You could sign up for 10.cash and it's free for a while until I add more features. And this is the link to the GitHub repo for that demo that I just showed. I could take a question, or should I be done? Okay, and you could ask me a question after or now, or yes.
Does this morphing tech work at all with like WebSockets and stuff, or is it just limited to web requests right now, or HTTP requests?
It's just HTTP requests. I mean, Turbo at least. Yeah, they have a way to broadcast changes to a client. So like if something changes on the back end, you want to tell a page, they have a way to broadcast that change over a WebSocket. But then it just fetches the page again over HTTP. Yeah. Live View does WebSockets for this stuff. Phoenix, Elixir folks. Yeah.
In terms of internet traffic, are you using more with this approach?
That's the trade-off, yeah. There's more traffic over the network. You're getting HTML back. But I mean, if you're not shipping React with your app to the client, you know, it might be you might be saving actually a lot of bytes just by sending the HTML. But you're right, it's more traffic. And if your network's slow, then your UI updates slow. So that's another trade-off.
So in the case of a slow network, how does it handle like race conditions on hydration if you are on mid-update and then a new server response comes?
Yeah. There is a way to cancel a request that's coming in. So that's how I think I would do it. I would say if the user refreshes again and there's already a request on its way, just cancel that and do a new one. I have that exact problem with the production app. So, and then yeah, if it takes a long time, there's some ARIA attributes that they add to the elements. So you can add some CSS that like dims the page. Maybe dims the form. If it's taking longer than like a second, you can dim it so that people know that it's not React. Okay, well, yeah, happy to talk afterwards, and yeah, thank you very much.
All right. By the way, there is a, if you watch my talk at RailsConf, there is an initiative about bringing optimistic UI to Hotwire. So that's something that would kind of solve a bunch of problems where for the user, it feels instant, the interactivity feels instant, but the update is actually happening on the background. Yeah, so there's a lot of community effort and the research, and there's a lot going on. You can go check out hotwire.io, where people also kind of gather a bunch of resources. So it's pretty cool. And yeah, that's amazing talks. And this concludes our programming for today. I'm super grateful for everyone who stayed pretty late. And let's continue, connecting, talking over there. And I'll see you at the next meetup.